little bit. I mean, I joined TMEIC about a year ago, but before I joined TMEIC, I was also doing the motor proposals for the other the motor companies. So my 10 years of experiences, I'm dealing with the motors on a daily basis, proposals and doing review the specs and technical data, things like that. So I'm going to turn off my camera because that may kind of cause some network issues here. So please understand. Okay, today I'm going to talk about starting strategies for large capacity motors. So I want to talk about what are the different starting methods that you can use for starting the large capacity motors. When we talk large capacity motors, it is typically in the medium voltage world about 2,000 horsepower and above. But based on the power system situations, it can be applicable to the motors, maybe 500 or 600 horsepower motors. But most certainly, the large capacity motors are like 5,000 or 6,000 horsepower motors and beyond. Okay, so now I have decided to use an electric motor to run the driven equipment, such as the compressors, pumps, fans, mills, etc. So then, how do I evaluate the motor starting system to run my electric motor for the driven equipment? In order to get the proper motor starting system, then I need to consider the followings. The first thing is, what are the power system availabilities and what are the limitations in terms of short circuit current availabilities, and what's the voltage drop that I can use for my electric motor and so forth. And the second thing is, I also need to look at what are the driven equipment requirements. Typically, the driven equipment requirements are dictated by the process or the driven equipment OEMs. And also, I need to look at what are the process requirements. I mean, do I need the fixed speed, or do I need the variable speed, or do I need somewhere in between? Things like that. So once I have these two pieces of information, then I can look at my motor starting schemes. Just please remember that I haven't decided yet what the motor starting method is going to be, but at least based on these two pieces of information, I can start looking at it. So which starting method will provide the best performance and efficiencies, and which will be the easy of use for the operators, and what are the physical size, especially the site has a very limited space, and how is it going to be maintained, and what are the reliabilities associated with my starting scheme. So I need to consider all of these factors when I'm making an evaluation. You may have a big question there. Why is starting large motors are so stressful? The first thing is, when you start the motor from the standstill, which is from the 0 speed, or you flip the switch to feed your electric motor, the motor is essentially appears as a short circuit to the power system. Okay, so whenever you start the motor from the 0 speed, it creates a lot of current. So because during the short circuit event, you almost have unlimited flow of electricity or current, and the voltage, which is the pressure on the utility bus, starts to go down. So remember that you have a high current at standstill. And also the second thing is starting current creates a lot of stresses in the windings of the electric motor, which are quite damaging. So you have may see an example that the customer's motors are burned out during the starting, or they're doing kind of repeated starting, then they only get like 10 or 15 years of the motor alive instead of getting 25 years of the motor design service life. So starting the motor directly on the line creates a lot of stresses and the motor windings. And third thing is the motor and the load must break away from the zero speed and should be able to accelerate to the rated speed. So when the motor is accelerate from the zero speed all the way up to the rated speed, it generates a lot of energy, and those kind of energies end up a form of the electric current. So remember, the current equals the heat for the motor. So all of those kind of short circuit current or extra current is not really being converted to the work. It's actually converted to the heat. So the heat is the main thing really can damage the motor or the motor windings. And those heat must be maintained in a proper way. Okay, that's the technical aspects for the motors, and then we also need to look at the technical commercial challenges from the end user standpoint. So you have to balance the allowed inrush amps with the voltage drop, and which means that you need to think about how much inrush amps are allowed for my electric motor versus the voltage drops that you're gonna see at the utility system. And also you need to balance the power system effects with the torque demand of the load. Because high starting torque application requires actually has very high starting current, which is leading to the much higher voltage drop. Okay, so also you need to balance the cost versus the benefits, I mean, associated with your choice of the starting method. So here we have four categories for the motor starting strategies. The first thing is a direct online, which is very common in our industries, and the reduced voltage starting method, and other mechanical starting method, and also a variable frequency drives starting method. We will look at each one more details in the next slides. Okay, direct online motor starting method. So this is a typical system configurations for the motors running at directly online. So you have some sort of utility voltages up to 13.8 kV. In North American market, typically you see 4160 volts or 6.6 kV. That's all the way up to 13.8 kV. And in some older installations, you may see like 2.3 or 2.4 kV. But anyways, we have some sort of utility voltages, and then you have an incoming circuit breaker or a fused vacuum contactor. Really depends on the ampacity that you want to pass through the circuit. Then you have an electric motor and your driven equipment. And you have here MPR, which is the motor protection relay, to make sure that the motor is protected during the starting or during the operating conditions. And here at the bottom, you see the typical motor speed torque curve. This green line here is the motor inrush current. Typical the current is 650% of the motor full load amps. That's where you see the highest current at zero speed. And this is your typical torque curve over the RPM. So directly online starting has some pros and cons. The pros are, of course, it's a simple starting method and a small footprint, and you have a lowest installation cost and the short acceleration times. The cons are as the following: because need a steep utility system and power capacity. You know, the starting current is 650% of the full load amps, which is very high. So you need a steep utility system. So steep utility system can be defined as the short circuit current to the load current ratio. So typically when you say steep, means maybe the ratio is about like 1,000 times of the load current. And then the weak utility system can be the ratio of short circuit current to the load current will be about 20 times. It's very weak. You can only get 20 times of the load current at the utility system. And the motor starting is limited to 2 cold, 1 hot consecutive starts. Of course, like if you are familiar with the API standards, it requires like extra starts, so 3 cold and 2 hot starts. But this is a typical DOL start as a kind of NEMA or IC standards. So the motor starts is limited to 2 cold and 1 hot. And also the power factor and efficiency are dictated by the motor. So once you design the motor for a specific power factor and efficiency at full load, full load or 75% or 50% of the load, it is fixed right there. And the motor speed is limited to 3,600 RPM. You may have some like emergency overspeed, like 20 or 25% for a certain time, maybe less than 2 minutes for the NEMA standard, but it is pretty much limited to 3,600 RPM. And also you have to look at the other considerations here. What are the available utility voltage level? What are the allowed voltage drops on the bus? Or what is the short circuit power capacity? Or the driven equipment tolerance to high starting or acceleration torques? Okay, so we talked about standard motor for the direct online starting. This is the same concept, but the motor with a low inrush current. So typical motor has a 650% inrush, but the low inrush current means we limited the current amps to 300 or 350%. This is very suitable for the offshore applications and or very weak utility systems. But note that the motor range capacity is very limited because if you lower your inrush current, actually your torque is going down as well. But most of the applications requires like high torque and then with a low inrush current. When we designed the motor for low inrush, in order to keep the torque up and the inrush down, we can use a different stator or rotor slot combinations. Or the most effective way is we use different the rotor bar materials. Instead of using a straight copper bar, we use the copper alloy bars like copper zinc 1537 or copper silicon bars. But those materials is helping the motor with the low inrush but a high torque. But at the same time, those materials creates a lot of hits. So to compensate the hit, we need to add more active materials like extra core pack, or if you reach the max core pack in the same frame, of course you have to increase the motor frame sizes like by 1 or 2 sizes. That's why it's very limited. The motor range capacity is very limited there. This is a typical motor data sheet that we TMEIC use. Of course, every motor vendor has their own format, but it is very similar to each other. So basically, you can see here the number of poles. This is a 4-pole, like synchronous RPM is 1500, and the voltage and the frequency. I want to talk about this here. Every motor data sheet comes with the locked rotor currents, what the motor is designed for. This one is designed for 600% locked rotor current. So which is, here is the point you can see the 600% of the full amps at 0 speed. Okay? That's we talked about in previous slide. And the starting method is DOL. The minimum start volts is 80%. I will talk about this a little bit more in details in the next slides. And here you can also see the starting duties. This motor is designed for 2 cold and 1 hot consecutive starts. So what are the actual starting duty means? I mean, of course, the motor is designed for Class F installation and Class B temperature. So what is the Class B temperature? Per the standard, we assume the ambient temperature as 40 degrees C, and we have like 80 degrees C as a temperaturized limit for the motor design. That gives us 120 degrees C, and then we have a 10 degrees C margin. So Class B temperature means it's like a maximum 130 degrees C, but for the motor itself, it is limited to 80 degrees C. So if we have a high ambient temperature, like 50 or 60 degrees C, then our temperature limit is 70 or 60 degrees C. So must be maintained below 120 degrees C. So we start the motor from the ambient temperature, which is the cold condition. That's the one start. So then if it was a successful start, then the motor temperature will be stabilized after a few hours here. But if that wasn't successful, then you have another chance to start the motor from that standpoint. So that's the second start. So then if that was a successful start, of course, the motor will be, temperature will be stabilized between pretty much, I mean, here the black dot or the red dot range. That's the two cold starts means. So what is the one hot start? So you run the motor from the cold ambient condition. So the motor is actually stable, temperature is stabilized. Here you see we call the hot condition. But for some reason that maybe you lost your power at the utility, or you have some lightning strike, or you just open the circuit and then reclose it, you still have another chance to start the motor from that hot condition. You don't have to wait for the motor to cool down to the cold condition. That's where you have the one start from the hot condition, then the motor temperature will be stabilized. But if the first hot start wasn't successful, so you didn't know how the motor was designed for, so you just hit it again. You had another second start from that hot temperature condition. So that is actually the motor is gonna be burned out. So you will damage the motor windings, because it's over the Class B temperature. So if that wasn't successful from the first start, you have to wait at least the motor temperature goes down to the hot condition level, which is the saturated motor temperature limit here. Then you have another hot start. Okay, just remember that you cannot damage the motor here. So please read the motor data carefully. Okay, the next starting method is a reduced voltage starting method. The reduced voltage starting also has 4 categories here: reactor capacitor, an auto transformer, and solid state starter, which is the soft to start the reduced voltage or reduced voltage soft start. So the first 3 reduced voltage starts, it's actually rarely used these days. We don't really use this method anymore. So we are not going to talk about all the details of the first 3 here, but the soft start, this is also used in our industry very commonly. So when you reduce the voltage starting, that means your motor torque is also reduced. So here's a quick equation for the voltage. So the torque is proportional to square root of the voltage, and the current is proportional to the voltage. So as an example, at 80% motor voltage, you only get 64% torque, like 0.8 times 0.8 is 0.64. And at 80% motor voltage, you get 480% inrush when if you have a 600% inrush at 100% voltage. So this is the key thing you have to remember. The reduced voltage starters do not change the motor frequency because the starter itself doesn't have a control over the speed. If you want that function, then you need to look at the VFD. So this is the example of the reduced voltage starts curve. This is the typical motor speed torque curve. These red lines are the current. You see here this is designed for 600% as an example here. Then this blue curve is the torque, and the pink is the load data. The point that I want to talk about here is, remember that I showed the motor data example that was designed for DOL at 80% of the minimum voltage, which means here the 80% torque. So when we design the motor, we make sure that we have enough torque margin, at least 10 or 15% margin between this 80% torque curve and the load data. So when we design for 80% reduced voltage here, the motor should be able to start without any interruptions. So if you want to start the motor at 70% reduced voltage here, there you only get 49% torque, right? This is the current, this is the torque. It's 0.7 times 0.7 is 79. So that's like really close to this load data, which means the motor will not start any interruptions. Because that means you have to bring the torque up. At the same time, your current will go up. So again, as kind of the low inrush design, so we have to balance how to keep the torque up and then also the current down. So that's that's very how it works. Okay. So reduced voltage starting. I'm not gonna talk about all the details here. This reactor method is not really used these days. So you have here the voltage comes in the reactor here to start the motor, and if the motor is accelerated to the rated speed, then you bypass and just run the motor as a DOL. So here, this is the typical speed torque curve of the reactor reduced voltage starting method. Here at maybe between 85 or 95 area here, you see the big bumps here, the motor current and the torque. There's a big peak. That's where we switch the motor over to the utility line. Okay, and it's a simple starting method, and of course you can reduce the inrush current compared to the DOL, and the reactor can be bypassed after syncing to the grid. But also you need to look at, you need the switch gear to bypass the reactor, and then it's not suitable for weak power systems. You need thorough evaluation of the power system and open transition to the utility line, which has we have a higher torque pulsation or torque vibrations. Also, you need to look at these considerations as the DOL motors. Another reactor capacitor starting method. The same, you use a reactor capacitor to start the motor all the way up to the rated speed, then you bypass. And then the same torque curve here, there's where we switch the motor, the utility line. The pros, cons, expensive, the same thing. So auto transformer, also, I'm not going to talk about all the details here. You use the auto transformer to start the motor and then totally bypass and the motor running at the DOL. Okay. I mean, of course, you can reduce the inrush current compared to the DOL, and the same approach, but it is very expensive and large footprints. It's not really used anymore these days. Now, soft starter, this is the main one we use in these days. If you cannot use the motor on the DOL, then we use a soft starter. So we use the soft starter, like the power semiconductors, to start the motor. And once again, then we bypass the motor running at the DOL. The speed torque curve here is very similar to the DOL machines, but here you see we reduced the inrush current from 650% to 350%. That's the typical numbers you may expect from the soft starter, and the others are the same. So this is a small footprint and cost-effective and reliable technology, but some negatives are, the limited time to ramp up the machine, because the soft starter actually has the max current limit for a certain limited time. So if you reach to max the current and your motor is not yet reached to the rated speed, but the starter is going to trip. So, and then it's not good for high starting torque requirements, or harmonic currents put back in the utility line, the power system studies. Anyways, also you need to look at other application considerations, like the available utility voltage level, what is the allowable voltage drop on the bus, and short circuit power capacity. This is another the mechanical starting method. This one is you use a pony motor to start your main electric motor. Remember one case was like this, and the pony motor itself was about over 2,000 horsepower motor. It was really big, and the motor was 20 megawatts, things like that. But again, even if you use the pony motor and then you have very weak power utility systems, you still may have to use the reduce the voltage starters here between utility line and the pony motor. So this is very special, very expensive, and a very large footprints. Okay, now we want to talk about the variable frequency drives starting method. I'm not a VFD expert, but my understanding is the VFD is the power conversion equipment. Okay. You have, any VFD is consists of these three components here, which the first thing is the converter section. You convert the AC to DC using diode or the IGBTs, which is the power semiconductors, right? And you have the energy storage section, which is also called a DC link. You use the inductor or a capacitor with the energy storage. So if you use the inductor here, that's current source inverters like CSI, and if you use capacitors, that's a voltage source inverters, VSI. Then you have inverter section. You convert the DC to the AC to feed your AC motors. Okay. And this is the typical, at the bottom here, typical electrical configuration. You have a utility mains, and then input breaker and step down isolation transformers, and the VFD. Based on the cooling system, we can design the VFD for air-cooled or water-cooled, and the motor and the driven equipment. But the key thing is the motor is suitable for like outdoor installations, but the VFD is the equipment that you must install indoor, and you have to maintain the circumstance very clean and cool. Okay. So why we use a VFD instead of the DOL or reduced voltage starting method? The main two key things are the current and the torque. You see here on the left side is a typical DOL speed torque curves, and here the variable frequency torque curves. As a DOL, you see 650% of the motor full load amps at 0 speed. But here, if you're using a VFD, you have almost 0 amps at the starting. Of course, it's not really 0, but close to 0, because you still have inertia and you have some static friction still have to overcome. But the point is, over this speed range, full range, you can manage the motor amps under the motor full load amps. That's a big benefit, right? And also the torque, until you get the the breakdown torque from the DOL starts, it's maybe 70 or 80% of the motor speed. You have to reach that. But here you have control over the frequency, means you have a control over the speed. So you have a very high starting torque from 0 speed. You can change this at any time. Those are the big benefits when you are using the VFD. Also, other benefits are you can start the large compressors, pumps, extruders, fans, and blowers at any time. I mean, especially the fans with a very high inertia. I mean, you can reduce the frame size by 2-3 size, and sometimes it's only limited to 1 cold, 1 hot starts. But if using the VFD, you can have unlimited starts anytime. And you can match the speed torque of the motor to the process. And you also have the energy savings by exploiting the 1, 2, 3, the fan laws. And then you can also improve in utility power factor, because when you start the motor on DOL, I mean, from the starting, you have really low power factor, maybe 0.5 or below. But if you're using the VFD, you can have the unity or very close to unity power factor at starting. Okay. But of course, the VFD is very, very expensive. I mean, it's more expensive than the motor. So that's another main concern for the end users. So here's the medium voltage ASD. The thing is, the input voltage can be anything. It can be 2.3 kV or 138 kV. So because voltage defined at the output. So ASD, VFD, EVFD, like a variable voltage, variable frequency, it's all the same thing. It's indicates the VFD. So here's the typical range of the VFDs. We have an air-cooled design and a water-cooled design, and there's some overlaps between like let's say 7,000 or 12,000 horsepower range. That's overlap. So when we design the VFD, of course we need to know what's the requirements. Like, do you really need a full-time VFD, or you only need the VFD for starting? What's the load speed torque curve, and what's the speed range of the requirements? And do you need the variable speed, or I mean, a variable torque or constant torque? What is your the overload requirements, things like that. So if it's a full-time VFD, of course, we need to include the utility people. But if only for the starting function, then we don't really have to talk to the utility people. We can just make a decision among the motor people, driven equipment manufacturer, and the EPCs. Here's okay. So one of the thing how you design for the motor starting duty, that is the you need to look at the VFD requirements. But typically that's for a certain short time, like for 60 seconds in every 600 seconds. That's happening in the shortened term. And what are the overload requirements? Typically we use like 110 or 115% for the pumps and blower fans, and some constant torque requirements applications like receipt compressors and mills like that. We use typically 150% overload. Okay. Okay. So we use like a fully loaded curve to design our motor for the VFD duty. Then of course we use a full rating. But if we can use unloaded curve to start the motor for VFD, it's a 70% difference in torque, then we can only size the VFD like a 30% here of the motor horsepower. Then I mentioned that we use like 110 or 115% overload for like a pump blower fan applications. Then if you only need the VFD to start the motor for shortened time, then we can consider that overload as well. So actually you need like a 25.5% of the rating, full rating to size your VFD. So it's really important to look at the curves on the requirements. So if you have the same voltage from a utility to VFD to the motor, that's the best fit. But some reason that the utility between the utility and the VFD, or the VFD and the motor has a different voltage level, then of course you need to look at the step up or step down transformers between. So that actually costs you more money. Here is a quick example of our 7500 horsepower Durabuild. You can use one drive to start multiple motor here. You can start the motor and then bypass and keep going up. But we highly recommend you to have like a backup, because if you only have one VFD, if that's failed, that's causing a lot of problems, and you may have a kind of money losses during the downtime. So it's good to have a backup as always. So how do we select the motor starting method properly? The first thing, does driven equipment require variable speed? If the answer is yes, then okay, variable speed is required, then you use a fully rated VFD to start. If the answer is no, we may ask, oh, can we start the motor as a DOL with a loaded condition? If the answer is yes, yeah, we can design the motor with the fully loaded condition. If it is not, we can use a full-time VFD, or we can ask the OEMs, the EPCs, end users, hey, can you please relook at the application and advise us if we can use unloaded curve to design our motor. If we can do that with unloaded curve, we can design it DOL with unloaded curve. If the answer is no, then can we use the reduced voltage start with the only unloaded curve? If we say yes, then we design the motor for reduced voltage starts. If the answer is no, then we use a smaller VFD as a soft starter. This is the kind of concept we have to apply for every motor design. Also, here are the key considerations besides this, and what is the available short circuit amps, what's the allowable voltage drop on the utility, and then the motor versus compressor or the pump speed torque capabilities, and what's the max allowable motor starts per hour. And then also you need to look at the torsional effect on the drivetrain, and then cost of the DOL motor versus VFD motor. Also, the VFD costs a lot of money compared to the motor, so that's the cost. You have to look at the cost comparison. And then what's the motor power factor as seen by utilities. So there's a lot of things you have to consider, but there's no yes or no answer here. So you have to look at all the possibilities to start to select the proper starting method for the motors. Okay, I thought I was gonna run up with the time, so from the middle of the point, I kind of moved very fast, but we still have like 15 or 16 minutes. So if you have any questions, please feel free to ask.
If you're shy and want to just do it as a chat, you can do that also.
Yes, I see that one question. Can you send the presentation deck out? Yes. The PowerPoint, this file is too big, so I will convert this to a PDF format, and I can send it out to all of you who attended this webinar today. So another question is, can you discuss a couple of motors designs we have? So you mean you have some examples that you want me to go over? But I doubt it if we have enough time to cover. But you can reach me at any time. I can give you I can provide my email address, phone number, whoever have any real questions.
There's another question, Jay, from Donald Ray. It's issues arise from starting an older direct across the line medium voltage motor with a VFD.
Can you repeat that again? I mean, the motor, the DOL motor that he wants to start from the VFD.
He has an existing, say he has an existing medium voltage motor that's currently being started at the line.
Okay.
Are there any issues with him putting a VFD on that motor?
Okay. I don't know if I understand correctly, but if I guess the existing motor is designed for the DOL, then he may want to use a VFD to start that motor. If you want to do that, of course, I mean, the VFD motor compared to the DOL motor, we do care about the motor, the insulation. For instance, if we have a 4160 voltage for the DOL motor, we use like a 4600 volt and the insulation class. But if we design that same voltage for the VFD motor, we may use like a 6 kV, the insulation voltage, to have the protection. Is that something
yeah, the motor needs to be designed for inverter duty rated. So it's all about that insulation. The old motors that he's got, I mean, he's got motors that are 50 years old. So,
okay.
So I'm sure that you got to be concerned about the insulation. Is there anything we could do, like put a reactor on the output, and then he could use the old motor?
I don't think so. I mean, it really depends on also if it's for hazardous area. That's another story. So I really need to look at the details. But basically, you cannot really use for the DOL motor for the VFD.
Don, I'll give you.
We'll get back to you on that.
Yeah. Jay, can you see the questions on the chat?
Yeah, I only see
Slide.
that.
You see Pablo's?
No, I only see two chats here. One was from the attendee 58. Can you send the presentation deck? I mentioned that. From the attendee 22, can you discuss a couple of motor design we have? That's all I see.
Huh.
Okay, I'll read the next one. There's a question from Rye Kennedy. are pony motors used at all for starting anymore?
Okay.
I have a comment on that. I have not seen a pony motor in my career except for one time. At Arnold Air Force Base, I was inside of one of their buildings and got a chance to look at a motor that powers a wind tunnel that is used for high-speed testing of jets or rockets or whatever. And I believe it goes up to Mach 6 or 7. And the actual motor is 186,000 horsepower. And the pony motor to start that motor was just under 20,000 horsepower. So, but that is the only time that I have come across a pony motor.
The next question, Pablo, your question about using step-down transformers between the VFD and the motor. The issue there is you need to make sure that the transformer is rated with a K factor to handle that application. So you need to work with the transformer manufacturer to make sure he sizes it properly. Jenna asked, are the direct online motors starting very common? If so, can you share some examples, industries they are used in? Yeah, Jenna, if you have a very strong, stiff electrical system, we see a lot of medium voltage motors started across the line. We do a lot in pulp and paper industry. And in there particularly, they start 3,000 horsepower motors across the line, like popcorn. Even if you have a weak distribution system, what ends up happening is the motor ends up acting as almost like an auto transformer starter. If it draws the voltage down, then so you may have a dip. It's all a question how much dip your power system can handle. Michael, you want to add Mike Redmond's question?
Sure. Mike Redmond asked, is the distance between the VFD and a motor still a factor?
Sure. Because I don't know if I have the correct number, but like 300 feet is kind of that we use as a standard for the cable length between the motor and the VFD. Of course, if it's over that, like you need a 1,000 feet distance. Of course, that is another factor we have to consider when we design the motor and the VFD.
Are there any other questions?
So much for attending. I'll send out a copy of the presentation.
And we also recorded it.
Go ahead.
We also recorded it, so we'll try and put a copy of the recording on our website also, which is
I will also convert the PowerPoint to PDF and forward that to Mike.
Great. Thanks, Jay. You did great.
Okay, thank you so much, everyone. I really appreciate for your time for today, and then hope to see you guys in the future. You never know. Thank you all. Be safe.